You've probably heard the line 100 times, nothing can go faster than light. It sounds like a rule carved into the universe by an unshakable hand, and for most people, that's where the conversation ends. But here's what almost nobody tells you. Physicists have spent over half a century asking a much stranger question. Not can we break the speed of light, but what happens on the other side of it, if anything does? And the answer they found is not science fiction. It's published, peer-reviewed, and in some cases it's mathematically required by the same equations that gave us the speed limit in the first place. Before this video ends, you're going to understand exactly what lives on the far side of that barrier, why one of the most respected physics experiments in modern history briefly convinced the world it had been broken, and why the truth turned out to be stranger than the mistake. Stay with me, because I want you to make a guess right now, before I tell you anything else. If something could exist beyond light speed, what do you think it would look like? Would it be visible? Would it carry energy? Would it even be matter at all? Hold that thought. You're going to want to compare it against what's actually sitting in the research, because I promise you, it's not what most people assume. Let's start with why this limit exists at all, because almost everyone gets the reason wrong. The common belief is that light speed is a kind of cosmic speed camera, an arbitrary ceiling the universe enforces the way a highway enforces 65 miles per hour. That's not what Einstein's 1905 paper on special relativity actually says. To understand where that paper even came from, you have to go back a few years earlier, to an experiment that quietly broke physics without anyone realizing it yet. In 1887, Albert Michelson and Edward Morley tried to detect the ether, a hypothetical medium physicists at the time assumed light needed to travel through, the same way sound needs air, or ripples need water. Their experiment split a single beam of light into two perpendicular paths using a device called an interferometer, bounced each half off mirrors, and recombined them, looking for the tiny timing mismatch that should appear if Earth's motion through the ether sped one beam up and slowed the other down. It's a beautifully simple idea on paper. They found nothing. No difference at all, no matter which direction they pointed the apparatus, no matter what time of year they ran it. For almost 2 decades, that null result sat there as an unsolved embarrassment, one of the most famous failed experiments in the history of science, cited constantly but explained by nobody, until Einstein resolved it in a single elegant stroke that didn't just patch the problem, it rebuilt physics from the ground up around it. There is no ether. The speed of light is constant for every observer, no matter how fast they're moving relative to anything else. That single assumption, stated almost like a throwaway line in his 1905 paper, is what unraveled everything we thought we knew about space and time. Here's the part that actually explains the speed limit, and it has nothing to do with light being special. It's about mass. As an object with mass accelerates, the energy required to push it faster increases, and it increases in a way that approaches infinity as its speed approaches the speed of light. Picture it this way. Getting a spacecraft from rest to half the speed of light takes an enormous but finite amount of energy. Getting it from half the speed of light to 90% takes dramatically more than that. Getting it from 99% to 100% doesn't just take more energy still, it takes an amount that climbs toward infinity, curving almost straight upward the closer you get to the line. There is no engine, no fuel source, no theoretical technology, however advanced, that could ever supply an infinite quantity of anything. That's not a rule someone wrote down on a chalkboard and declared a law by decree. That's a wall built directly into the mathematics of energy and motion itself. Light has no rest mass, which is precisely why it's allowed to travel at that speed without needing any energy input to sustain it, and precisely why nothing with mass can ever catch up to it, no matter how much energy you throw at the problem. This is where almost every documentary on this topic stops. But the equations themselves don't stop there, and neither should we. In 1962, 3 physicists named Oleksandr Miron-Bilanuk, Vandana Gudial-Deshpande, and George Sudarshan published a paper asking a deceptively simple question. What happens if you don't try to accelerate an object up to the speed of light, but instead imagine something that has never, in its entire existence, moved at any speed slower than light? 5 years later, physicist Gerald Feinberg picked up that idea, formalized the mathematics, and gave it a name that has stuck in physics ever since, the tachyon, from the Greek word for swift. Now, before you picture some kind of superhero bullet or a beam weapon from a comic book, understand what the actual mathematics of a tachyon requires, because this is the answer to the guess I asked you to make earlier. Einstein's equations relate mass, energy and velocity through a term that includes the square root of 1 minus velocity squared divided by the speed of light squared. For an object moving slower than light, the number under that square root is positive, and everything behaves the way you'd expect. For an object moving exactly at light speed, that number hits zero, which is why photons can travel at that speed with zero rest mass, and the equation still balances. But plug in a velocity greater than light speed, and the number under the square root becomes negative. And the square root of a negative number is what mathematicians call an imaginary number, represented by the symbol I, the square root of -1. This is the part where most explainer videos wave their hands and move on, but I want you to actually sit with it. For a tachyon's math to work out, physicists proposed that its rest mass itself would have to be imaginary. When you multiply an imaginary mass by that imaginary term under the square root, the two cancel each other out, and what emerges on the other side is a perfectly real, positive, physical energy value. Read that again. The equations don't collapse beyond light speed. They reorganize. A particle with imaginary rest mass, moving faster than light, produces completely real, measurable physical properties. That's the honest, cited answer to what relativity mathematically permits beyond the barrier. Not fantasy, not a loophole someone snuck in. A consistent, if deeply strange, extension of the exact same equations that gave us the speed limit to begin with. But here's the myth I need to correct immediately, because it's one of the most common ones floating around online. A tachyon isn't just strange, it's also strange in a way that creates a genuine problem for cause and effect. If a tachyon could carry a signal, and certain reference frames view faster than light signals as traveling backward in time, then in principle you could construct a version of the grandfather paradox using tachyons instead of a time machine, sending information into your own past. Physicists take this seriously enough that it's one of the strongest arguments used against tachyons ever being real, functional carriers of information, even if they exist mathematically. Here's roughly how the paradox works, and I want you to actually follow the logic rather than just take my word for it. Special relativity tells us that different observers, moving at different speeds relative to each other, don't always agree on the order in which two events happened, as long as those events couldn't have influenced each other through an ordinary, light speed or slower signal. Normally this doesn't matter, because nothing can send that signal faster than light anyway, so cause always precedes effect for everyone, no matter their perspective. But a tachyon breaks that safety net. If a tachyon signal could genuinely be sent and received, there exists a valid, physically legal reference frame in which that signal arrives before it was ever transmitted. Send yourself a tachyon message, arrange for your past self to receive it and act on it, and you've built a working paradox machine using nothing but particles physics doesn't actually forbid on paper. This is sometimes called the reinterpretation principle, and different physicists resolve it differently. Some arguing tachyons simply can't carry information even if they exist. Others arguing the paradox is proof tachyons can't exist as real objects at all, which is exactly the kind of unresolved disagreement worth sitting with rather than smoothing over into a tidy, false certainty. So is any of this observed? No tachyon has ever been detected. Not once, not in any particle accelerator, not in any cosmic ray detector, not anywhere on Earth or in astronomical observation. Feinberg's 1967 paper was a theoretical proposal, and it kicked off decades of genuine experimental hunting, not just idle speculation. Physicists have searched cosmic ray showers for tracks consistent with tachyonic particles. They've built dedicated detectors specifically designed to catch a tachyon signature if one ever passed through. And more quietly, several major neutrino experiments, including measurements at facilities like MINOS in the United States and Super-Kamiokande in Japan, have occasionally reported neutrino mass-squared values that came out slightly negative in early, imprecise runs, which is exactly the mathematical fingerprint a tachyon would leave behind, since a negative mass-squared is just another way of describing an imaginary mass. Every single one of those anomalous readings, without exception, was later resolved as a statistical fluctuation or a measurement uncertainty once the data collection improved. Not one has held up. So the honest scientific position, stated as plainly as it can be, is this. The tachyon remains a mathematically consistent idea that keeps almost showing up in the data and then vanishing every single time anyone looks closer. That's not the same as it being disproven. It's something stranger. It's a hypothesis that refuses to either confirm itself or fully die. So if you've seen a video or a forum post confidently claiming scientists have found particles moving faster than light, that claim is false, at least so far. And at least so far is doing real work in that sentence. And there's a very specific, very famous reason that myth keeps resurfacing, and it involves one of the most dramatic reversals in modern physics. In September 2011, a collaboration called OPERA, based at the Gran Sasso Underground Laboratory in Italy, announced something that made headlines around the world. They had been firing neutrinos from CERN in Switzerland to their detector in Italy, a distance of roughly 730 kilometers, and their timing measurements suggested the neutrinos had arrived 60 nanoseconds earlier than light would have covered that same distance. 60 billionths of a second. That's an almost absurdly small number, but it was enough, if accurate, to mean the neutrinos had genuinely outrun light itself. The scientific community did not celebrate. It got suspicious, immediately and appropriately, because a result this enormous demands proof this solid, and extraordinary claims in physics live or die on exactly that standard. Here's the human cost side of the story, because it matters, and because it's a better lesson than the anomaly itself. The physicists on the OPERA team did not rush to claim a Nobel-level discovery. They published their data openly, and their spokesperson explicitly told the press that the collaboration could not yet explain the result themselves, and was inviting independent labs worldwide to check the measurement. That's what rigorous science actually looks like. Not certainty announced with confidence. Transparency admitted with discomfort. And within months, the answer came back, and it wasn't cosmic at all. Investigators traced the discrepancy to two separate hardware issues: a loose fiber optic cable connector at one end of the timing system, and a clock oscillator running slightly out of synchronization with the GPS signal used to coordinate the measurement. Once both issues were corrected, the neutrinos arrived exactly on schedule, exactly at light speed. No faster, no exceptions. Think about what that team actually went through for those few months. Every major news outlet on the planet ran the story. Physicists who had spent entire careers building relativity's foundation were suddenly fielding questions from journalists asking if Einstein had simply been wrong the whole time. Rival labs at Fermilab in the United States and elsewhere immediately began independent attempts to replicate or refute the measurement, exactly the way healthy science is supposed to respond to a shocking claim. Inside the collaboration itself, some members reportedly disagreed about whether the results should have been announced publicly at all before more internal checks were run, which tells you that even the scientists closest to the data weren't unanimous about how confident they should sound. The physicist who had led the OPERA collaboration resigned from that leadership position shortly afterward, not because of any misconduct, but because of the sheer intensity of public fallout from a result that had briefly convinced the entire world that the impossible had happened. It's a sobering reminder that even careful, well-intentioned science can be derailed by something as mundane as a loose cable, and that real credibility comes from correcting yourself loudly in public, not from quietly hoping nobody checks your work. Now, here's a twist inside this story that almost never gets mentioned, and it's the beginning of a thread I'm going to leave open for you at the end of this video. Not every faster-than-light claim in physics is automatically false, and not every instance of something moving faster than light is even controversial. There's a real, observed, entirely mainstream phenomenon called Cherenkov radiation, named after Soviet physicist Pavel Cherenkov, who won the Nobel Prize in 1958 for explaining it. When charged particles travel through a medium like water or glass, the speed of light itself slows down inside that medium, sometimes dramatically. That means a particle can absolutely travel faster than light is currently moving inside that specific medium, without violating relativity at all, because it's still moving slower than light speed in a vacuum. This produces a faint, eerie blue glow you can actually see with your own eyes in the water surrounding certain nuclear reactor cores. And it's one of the most photographed phenomena in experimental physics, precisely because it looks like something out of fiction while being entirely mundane, well-understood engineering. It's essentially a light-speed version of a sonic boom. When an aircraft exceeds the speed of sound in air, it produces a shockwave cone you can hear as a boom. When a charged particle exceeds the local speed of light in water or glass, it produces a shockwave of light instead, radiating outward as that characteristic blue cone. Cherenkov detectors built around this exact principle are used constantly in modern neutrino observatories, including the very facilities that hunt for tachyonic mass signatures I mentioned earlier. Which means this faster-than-light phenomenon isn't just real, it's actively one of the tools physicists use to study everything else in this video. So here's your misconception correction for the day. Faster than the local speed of light in a medium happens constantly and is completely uncontroversial. Faster than light in a vacuum has never been observed once. Those are two completely different claims, and conflating them is exactly how a lot of faster than light misinformation spreads across the internet. So if tachyons remain purely theoretical, and the one experiment that seemed to break the barrier turned out to be a wiring fault, does the story end there in a kind of shrug? Not even close. Because there's a second path around the light barrier that isn't theoretical fantasy at all, and it's being actively researched right now by physicists with real funding, real published papers, and real institutional backing. This is the part I actually want you to argue with me about in the comments, because even physicists disagree about how honestly this should be described to the public. Here's the trick. Special relativity's speed limit governs objects moving through space. It says absolutely nothing about the speed at which space itself is allowed to expand, contract, or warp. In 1994, a Mexican theoretical physicist named Miguel Alcubierre published a paper built on exactly this loophole. Instead of accelerating a spacecraft to a faster than light speed, you construct a localized bubble of space around the spacecraft, contract the space in front of it, expand the space behind it, and let the bubble itself carry the ship forward at an effective speed greater than light, while the ship inside the bubble never locally exceeds light speed at all. Nothing inside the bubble breaks Einstein's rule. The rule is satisfied perfectly at every single point in the equation. It's the space around the rule that's doing the moving, not anything traveling through it. This is called the Alcubierre warp drive. And yes, the name is a deliberate nod to the kind of faster-than-light travel long imagined in science fiction. But I want to be very clear about something before we go further. This isn't a fictional concept borrowed for a physics paper as a marketing gimmick. Alcubierre was a working theoretical physicist solving Einstein's actual field equations, the same equations that describe black holes and the expansion of the universe. And he found a mathematically valid solution that happened to produce exactly the kind of effect that decades of storytellers had only been able to imagine. That's a genuinely remarkable thing for a piece of published physics to do. And it's exactly why this paper still gets cited today, more than 30 years after it came out. I want to be completely honest with you about exactly where it stands today though, because a lot of channels oversell this and I'm not going to be one of them. The math works and it's taken seriously in mainstream physics journals. NASA's EagleWorks laboratories under physicist Harold White published follow-up research through the 2000s exploring modified versions of Alcubierre's geometry, specifically aimed at reducing its energy requirements. But Alcubierre's original 1994 proposal required an amount of exotic negative energy density that, in its first form, exceeded the total mass energy of the entire observable universe. Later refinements brought that number down substantially, with some proposals theoretically approaching something closer to the mass of a moderately sized planet rather than an entire universe. Which sounds like progress, and in a sense it is. But that's still a form of matter with negative energy density that has never been produced, confirmed, or even convincingly theorized as physically obtainable in any laboratory on Earth. There's also a deeper objection raised by physicist Stephen Hawking, sometimes called the chronology protection conjecture, which suggests the universe may have built-in mechanisms that prevent exactly this kind of spacetime manipulation from ever being stable enough to use for actual travel, let alone travel that could be twisted into a time machine. So here's the honest reality check, stated as plainly as I can put it. The mathematics of moving faster than light without breaking relativity is real, published, and taken seriously by credible physicists. The engineering to actually build it does not exist, and quite possibly cannot exist, for reasons written into the same equations that made the idea possible in the first place. Let's pull one more thread, because I promised you a resolved answer, not just a pile of loosely connected theories. And there's a phenomenon that gets misquoted online more than almost anything else in modern physics: quantum entanglement. This one actually goes back to Einstein himself, which surprises a lot of people, since he's usually cast as the person who built the light-speed wall in the first place, not the one poking at it. In 1935, Einstein, along with physicists Boris Podolsky and Nathan Rosen, published what's now called the EPR paper, arguing that quantum mechanics, as it was then understood, seemed to require an effect that Einstein found deeply uncomfortable: a connection between distant particles that appeared to act faster than any signal could physically travel between them. Einstein wasn't proposing this as something real to celebrate. He was using it as an objection, essentially arguing that if quantum mechanics predicted this, quantum mechanics must be an incomplete description of reality, because he considered instantaneous influence across a distance to be physically absurd. For decades, that argument sat unresolved, a philosophical disagreement more than a testable one, until physicist John Stuart Bell developed a mathematical framework in 1964 that finally made it possible to actually test who was right in a laboratory, rather than just argue about it in a seminar room. You've probably heard someone claim that entangled particles communicate instantly, faster than light, no matter the distance separating them. That claim is technically true and deeply misleading at the exact same time. And here's the correction you need. When two particles are entangled and you measure one, the state of the other does appear to resolve instantaneously, regardless of distance. And this has been confirmed experimentally in landmark loophole-free Bell test experiments conducted in 2015 by a team at Delft University of Technology led by physicist Ronald Hansen, with similar independent confirmations from labs in Vienna and the United States that same year. But here's the catch that resolves the mystery instead of leaving it hanging open. You cannot use this effect to send information. The outcome of your measurement is fundamentally random. You have no way to control which state your particle collapses into, which means you have absolutely no way to encode a deliberate message inside it. Your partner, measuring the other particle at the same instant, only sees the correlation once you later compare notes through an ordinary light-speed limited channel, a phone call, an email, a satellite link. No usable information ever crosses the distance faster than light. The connection between the particles is completely real. The communication between the people holding them is not. That's the reality check, and it's the exact reason physicists get visibly frustrated when entanglement gets described as faster than light messaging in headlines. So let's bring this all together, because you deserve a clear answer, not just a tour through interesting ideas that never lands anywhere. What's actually beyond light speed? Mathematically, tachyons, particles with imaginary rest mass that produce entirely real energy values, remain a permitted but completely unobserved solution to relativity's own equations, and they carry a built-in causality problem that makes many physicists doubt they could ever function as real information carriers even if they exist. Experimentally, no particle has ever been measured exceeding light speed in a vacuum, and the one famous case that seemed to prove otherwise was traced back to a faulty fiber optic connector, not new physics. While genuine faster-than-light motion inside a slowed medium, Cherenkov radiation, is real, observed, and completely uncontroversial, precisely because it isn't breaking the vacuum limit at all. Geometrically, the Alcubierre warp metric shows that space itself is not bound by the same speed restriction as objects moving within it, opening a theoretically valid but currently unbuildable and possibly forbidden path to effective faster-than-light travel. And quantum mechanically, entangled particles produce a correlation that looks instantaneous but carries zero usable information, meaning it never actually violates the light barrier at all, no matter how many headlines claim otherwise. 4 different frontiers of physics, 4 different answers, 0 science fiction. Every single one of them cited, published, and still being actively debated in journals today by working scientists who get paid to disagree with each other in careful, peer-reviewed detail rather than in comment sections. And notice what all 4 of these answers have in common, because I think it's actually the most important pattern in this entire video. None of them are a simple yes. None of them are a simple no either. Every single frontier we just walked through resolves into a conditional, carefully qualified truth. And that's not physicists being evasive. That's what honest, evidence-based reasoning actually looks like when it's done properly, instead of flattened into a headline built for clicks. Now here's where I want to be honest with you about something else entirely, because this channel survives on more than just views. Every one of these episodes takes real research time. Tracking down the original 1962 Bilaniuk, Deshpande and Sudarshan paper, verifying the exact resignation details from the opera collaboration rather than repeating a second-hand summary, cross-checking Alcubierre's original 1994 energy requirements against Harold White's later revisions, so I'm not handing you a number that's already years out of date. If you've made it this far and you've found real value in getting the sourced, corrected version of a story instead of the recycled myth, a super thanks on this video goes directly toward keeping that kind of digging possible on a daily upload schedule. I'm not going to pretend this is a small ask, and I'm not going to bury it under a vague "consider supporting the channel" line. It genuinely helps, and I'd rather tell you that plainly than pretend this content assembles itself for free. Before you go, I want you to actually think about something, because I don't want this to be a video you watched once and immediately forgot. Go back to the guess I asked you to make at the very start. Did you picture something closer to the tachyon, an invisible particle defined by an imaginary mass? Or did you picture something closer to the warp bubble, a trick of geometry rather than a trick of speed? Tell me in the comments which one surprised you more, and while you're down there, argue with me if you think I'm wrong about how seriously the warp drive research deserves to be taken. Some physicists think even discussing it publicly creates false hope that distracts from real, fundable research. Others think dismissing it too early is exactly how genuine breakthroughs get starved of attention in their most fragile early years. I don't think there's an easy answer here, and I would honestly rather you disagree with me in the comments than just scroll past and forget the question entirely. Here's what I haven't told you yet, and it's the reason you should come back tomorrow. In that same year, 2011, while the opera anomaly was making global headlines, a completely different measurement using a completely different method at a completely different facility quietly produced a discrepancy in neutrino mass data that had nothing to do with the loose cable and has never been fully resolved to this day. Tomorrow we go back into that specific dataset and I'll show you the exact number that still doesn't add up.